Lesson 20 is transformations of trig functions, and before we get into different transformations applied to trig functions, I just want to review the transformations just like kind of in a more general sense. So this formula is the transformation formula for just like general function notation. So it's a times f of 1 over bx minus h plus k. A indicates a vertical dilation, b indicates a horizontal dilation, H will be a horizontal translation and K will be a vertical translation. Translations are when the graph is shifted up, down, left, or right, but the shape of the graph does not change in any way. So it won't become like more steep, more narrow, anything like that. With a dilation, that's like a stretch or compression. Vertical would be like towards the x-axis, like pulling something up and away, or like kind of pushing it down towards the x-axis. Horizontal would be pulling or pushing towards or away from the y-axis. With dilations, though, big thing is that the shape of the graph will change. Not like drastically, I guess it'll be the same like overall shape, but like the steepness of the graph may change, or like how narrow, how flat different areas are. Those parts will all change with the dilation. Okay, so 20.1, this is just translations of trig functions. So starting off with vertical translations. So vertical translation, so what this example says, the following graph is f of x equals 4 cosine of x. Apply the transformation g of x equals f of x plus 2, and then write the function rule for g of x. So this part right here, g of x equals f of x plus 2, is telling us everything we need to know about what transformation is being applied. We just have to kind of translate it into different terms to make sense of it. So in order to figure out what transformation is being applied, we look at, okay, what change is happening to f of x? And in this case, it's a 2 that's being added at the end of f of x. So when you have a constant that's being added to the end of f of x, that's going to be k. So it's a vertical translation. I know it's in the vertical translation section, so it's like duh, but not everything is just going to be like perfectly labeled like that. So if you see a number added after f of x, that's going to be a vertical translation, and vertical translations are straightforward and like up down kind of, because there's a plus in front of the k. It's different for horizontal translations, but k has a plus in front of it, so that means like if you see a plus 2 here, you're just going up 2. If you see a minus 2, you'd be going down 2. You don't have to worry about any sort of like kind of trick with vertical translations. Okay, so translation means that all the points are just shifting up 2 units. So instead of watching me try to like struggle through moving all of these points up 2 units, I'm just going to show the graph like being slid up 2 units. So if we kind of just focus in on one of the maximums, if I move it up 1 unit, it'd be up here, 2 units would be up here, and that is a vertical translation up 2 units. So in Canvas, you'll be just kind of presented with, say, like 4 different graphs to choose from, and you have to decide which one is like the graph translated up 2 units. So you won't have to worry about graphing them from scratch necessarily, so I didn't really worry too much about it here. But the pink graph is going to be my g of x, and that is f of x translated up 2. And then I just need to write a function rule for g of x. And so to do that, I'm just going to copy down this little formula first. So it's g of x equals f of x plus 2. And that means that I can just take what was f of x, which is 4 cosine of x, and I can just put it in here and then add the 2 at the end, and that'll give me my rule for g of x. So it'll be g of x equals, instead of f of x, I'll put the 4 cosine of x in there. Could put the x in or out, parentheses, doesn't matter, and then plus 2 at the end, and there's no simplifying we can really do here. So it'll just be g of x equals 4 cosine of x plus 2. Okay, and then horizontal translations on the right side. So for horizontal translations, it says the following graph is f of x equals 4 cosine of x. It's the same original function as with the vertical translation section. Apply the following transformation of g of x equals f of x minus pi over 2, and then write the function rule for g of x. So same kind of approach. We want to figure out, okay, what change is happening to our f of x. In this case, it's a change that's happening inside the parentheses. So we kind of look inside of our parentheses up here. We're looking at, okay, is something being multiplied by x? No, it's being subtracted from x. So it must be a horizontal translation. So it's going to be some sort of h. And then we have to kind of decide, okay, like what is the value of h? And this is kind of like the spot where the most mistakes get made, because this minus inside here is just, it's a part of the formula, which means that this minus is also a part of the formula, which means that h is just going to be like regular pi over 2. Not negative pi, like positive pi over 2, not negative pi over 2. So with h, it's kind of like always the opposite of what it looks like it should be in your like function or in the like transformation rule. So since we had a minus inside here, h is going to be positive. If we saw a plus inside there, h would be negative. So since h is positive, we'd be going to the right. So we're going to go pi over 2 to the right. Okay, so if we have to go pi over 2 to the right, we have to figure out, okay, how many units is that? So pi over 2 just means half of pi. So pi over 2 is half of pi. So if you see a problem like this, and you don't see pi over 2 directly labeled on the x-axis, I would recommend finding pi and then finding half of that distance, and that's how much we're going to translate. So pi is right here, which unfortunately is not on an exact mark, but I think that's part of why they threw this problem in there. So it's, let's see, 1 unit, 2 units, and then after like the third kind of unit on there, then there's pi, so it's a little bit more than 3. So half of that would be like a little bit more than 1.5. It's really just like, oh, not what I meant to do. It's really just like where this crosses the x-axis right there. That's our like halfway point. So that's the distance that we have to translate everything to the right. And again, you won't have to do it from scratch. You'll be presented with like a bunch of different graphs that you just have to choose which one has the correct translation. So I'm just going to take this graph and kind of slide it to the right by that distance. So if I move everything pi over 2 to the right, it's going to end up about right there. And again, it's just a sketch. It doesn't have to be necessarily perfect. We just want to make sure that we're able to identify, like, is the distance correct? Does it make sense in this context? I know like from here to here, that was pi. I just needed to go half of that distance, which it looks like that's what I did. From here to here, it looks about half that distance. So pi over 2. So this has that correct translation in there. So everything is shifted pi over 2 to the right, and then we just want to write the function rule. So I'm going to treat it the same way. I'm just going to kind of copy down this little transformation rule down below. So it's g of x equals f of x minus pi over 2. And I'm going to go ahead and copy down f of x for this one just so I can kind of zoom in and reference it a little bit better, because these ones are a little bit more tricky. So it'd be f of x equals 4 cosine of x was f of x. Okay, so when you have a change that's happening inside the parentheses, it's called like inside the argument. So f of x minus pi over 2, that means that that whole thing replaces x. So we take out the x in the original f of x and we swap it out for x minus pi over 2. So it'll be g of x equals, all of this will stay the same, so think of that as like kind of like a template. So it'll be 4 cosine, but that's instead of just regular x, it'll be of x minus pi over 2. Because we took out the x and we put x minus pi over 2 in there. Okay, so it'll be g of x equals 4 cosine of x minus pi over 2. Okay, moving down to 20.2, this is dilations of trig functions. So we'll start with vertical dilations. So the following graph is f of x equals 2 sine of x, apply the transformation, g of x equals 3 times f of x, and then write the function rule for g of x. So same approach, we have to look, okay, like what change are they applying to f of x? In this case, we're multiplying a number out in front of f of x. So if we go back up here, when you have a number multiplied out in front of f of x, that's a vertical dilation. So it's going to be a vertical dilation by that scale factor. So let's see. That scale factor in this case is 3. So that's going to be our A. That's how much we're going to stretch everything vertically by. When you stretch things vertically, you multiply the y coordinate, because the y coordinate is like the kind of vertical part of the point. So let's see. I'm going to kind of grab like a few key points from this graph. This one I couldn't like really drag because it's going to change the shape of it. But let's say I have this point right here. That's my maximum. That looks like pi over 2, 2. And then like my minimum down here, I'm going to say that's 3 pi over 2 because it's halfway between 1 and 2 pi, and then negative 2. Okay, so what a vertical dilation does is it multiplies the y coordinate by that scale factor. So I'm going to do like 2 times 3 is 6, and then that's going to be my new point's y coordinate. So it's going to take this point and it's going to stretch it up to pi over 2 and then 6 all the way up here. So the x coordinate is not going to change at all. Just the y coordinate is going to get tripled in this case since the scale factor is 3. And then the same thing kind of happens with this one down here. Really, like, it happens to all of the points, but we just want to get kind of like a few down to get a feel for how the shape of the graph is going to change. So I do negative 2 times 3, the scale factor, so that becomes negative 6. So that point, 3 pi over 2 gets pulled downward and becomes 3 pi over 2, and then the y coordinate becomes negative 6. So whenever vertical dilation occurs, just every point on the graph is going to get pulled either up or down away from the x-axis by, in this case, a factor of 3. So like 2 times 3 to get 6, negative 2 times 3 to get negative 6. And since we kind of pulled out our like maximum and minimums, that's going to be the same for all of the maximum and minimums. They're all going to get pulled to a height of 6 or negative 6. So like this one, I can pull straight up right here. I think that's a little bit off. This one, I can pull straight up and put a height of 6 right there. Let's see, this guy I could pull down. And then, this one I can pull down and become negative 6 down there. My max up here I can pull up to a positive 6. This minimum I can pull down to a negative 6. This maximum I can pull up to a positive 6 up here. And then from there we can connect all of our new points. So I'm going to go ahead and erase these ones that I was kind of just using to point out. And in this case, since we're like multiplying in a scale factor that's greater than 1, you should see the graph get stretched. One thing I'm going to add in though that will not change is none of the x-intercepts will change. And it's not just like one of those random math feeling things. The reason the x-intercepts don't change is because like this is pi, but the y coordinate is 0. And so if I take that 0 and I multiply it by the scale factor 3, it's still 0. So those are some kind of free points that stay. All the y-intercepts will stay exactly the same. So we can include, all the x-intercepts will stay exactly the same. So we can add those in, and then we can begin to connect our points. So you can see like our graph gets like pretty, like a lot steeper, maybe more narrow, depending on how you're thinking of it. And that's because it's getting stretched and pulled up and away from the x-axis. Okay, so picture like, it's kind of hard to like, I can't show my hands on here, but like you're pulling all of the maxes and the minimums like vertically away from the x-axis. Okay, and then writing our function rule, I'm not going to rewrite the transformation rule down again, but it's g of x equals 3 times f of x, and so what that means is we just have to take a 3 and multiply it by the original f of x to get g of x. So it'd be g of x equals, I just need to multiply the 3 by the 2. So 3 times 2 is 6, and then sine of x. And if you think about this like kind of as from a whole unit like visual, when we have a 6 out in front, like that means our amplitude is 6. And if we look back at our graph, like our midline is y equals 0, and the amplitude up to the maximum or down to the minimum is 6 as well. So it's all like kind of full circle and connected. Moving on to horizontal dilations, it says the following graph is f of x equals 2 sine of x, so same original function as we had for vertical dilations. Apply the transformation g of x equals f of 1/3 x, and then write the function rule for g of x. So to figure out what type of transformation we're applying, we're looking, okay, like where is the change happening? It's a number that's being multiplied by x inside the parentheses. So if we go up here, when you have a number that's being multiplied by x inside the parentheses, that's the vertical dilation. And because it's 1 over b in the kind of function notation, that means that b is going to be like the opposite, or not the opposite, but the reciprocal of what you see in there, since you see 1 over b. So since there's a 1/3 being multiplied by x, then b would be just the reciprocal of that, so it would just be 3. So b is 3. And since this is a horizontal dilation, that means that it's going to be stretched horizontally away from the y-axis. And I'll be honest, I like tried to graph this and it made it way more confusing and like kind of, it was just difficult to keep it clean. So I'm going to show it with Desmos. Before we do that, I'm going to write the function rule for g of x. So the kind of our transformation rule was g of x equals f of 1/3 x, and I'm going to rewrite f of x down here as well. So it's f of x equals 2 sine of x. And when you have a change that's happening inside the parentheses with the x, that's called like inside the argument. And so that completely replaces x in f of x to get your new function. So we'll have 1/3 x in here instead of just a regular x. So it would be g of x equals, everything else is going to stay the same, so it'll be 2 sine, and then instead of x, it'll be 1/3 x. So g of x equals 2 sine 1/3 x, and like I said, this is going to be a horizontal stretch since the scale factor is greater than 1. So I'm going to switch over to Desmos. Okay, so right now is just the original function y equals 2 sine of x, and then I'm gonna click on the like transform function, the one that's supposed to be a horizontal stretch. So you can see the blue function, the new one, is getting like kind of pulled out wider, like away from the y-axis. And then I just want to focus in on like kind of a few points and how they're changing. So when you change by a horizontal dilation, it's the y coordinates that are getting multiplied, or sorry, excuse me, it's the x coordinates that are getting multiplied by the scale factor instead of the y coordinates. So vertical dilation, the y coordinate change because that affects the height of the point. Horizontal dilation, the x coordinates change because that affects the width of the point. So like if I look at this point right here is pi 0, and I was supposed to apply a stretch of like a scale factor of 3 to the x coordinate. So that point right there gets stretched over to this point, which is 3 pi 0. So I took pi and I multiplied it by 3. That point, the 3 pi is like kind of the same location in the cycle. It's that like second midline point or second x-intercept of the sine cycle. Another pair of points that changes, so this is pi over 2, and it gets stretched over to the like new maximum 3 pi over 2 for the x coordinate. So we're taking pi over 2 and multiplying it by the scale factor 3 to get that like stretched out maximum on that blue line. Okay, so looking at these two as a whole, I'm not going to draw on the horizontal dilation. It'll just end up being kind of like, I guess, flatter a little bit. Then the like original function just got pulled out sideways. One thing I do want you to make a note, if you don't already like have it, is that for vertical dilations, you multiply the y coordinate by the scale factor, and then for horizontal dilations, you multiply the x coordinate. Okay, moving down to 20.3, these ones will go pretty quick. So transformation rules for trig functions. Example 1 says the function f of x equals 3 cosine of 2x plus 4 is transformed by the rule g of x equals f of x plus 5. What is the function rule for g of x? So it just means that we have to take this transformation and kind of put it in our actual like f of x function. So we talked about before how like if there's a change happening inside the parentheses or inside the argument, that means that x gets replaced with it. So f of x plus 5, instead of having an x there, we're going to take out the x and put in x plus 5. So everything else will stay the same. There'll still be like all of this, the plus 4 at the end. We'll just have to take out x and put in x plus 5. So it'd be g of x equals 3 cosine, and then parentheses 2, and actually if you want to use brackets for now, might help keep it a little cleaner. But so brackets, and then there's the 2. So up until now, we've just done like 3 cosine of 2. And then now we've gone to the x part. So now we're going to put in the x plus 5. And then we'll close out the parentheses and the brackets after the x plus 5. And then that plus 4 will get added to the end. So everything else in the function has stayed the same, the 3 cosine with the 2, and then the plus 4 at the end. It's just the x got swapped out for x plus 5, and then now we just need to simplify, so we need to go ahead and distribute the 2 in. So it'd be g of x equals 3 cosine, and then if I distribute the 2 in, it'd be 2 times x, and then 2 times 5. So parentheses now, since I don't need to like double up, 2 x and then plus 2 times 5, so plus 10. We'll close parentheses and then plus 4. And then that'll be it. We won't like add the 10 and the 4 since the 2x plus 10, those are inside of the argument, and that just stays there. We can't simplify beyond that. So it'd be g of x equals 3 cosine of 2x plus 10 and then plus 4. Moving on to example 2, the function f of x equals cosine of 3x plus 1 is transformed by the rule g of x equals 5 times f of x. What is the function rule for g of x? So it says g of x equals 5 times f of x. So that means that we have to take 5 and we have to multiply it by like all of f of x. So that can be kind of easy to like forget that. We have to include like every single part of f of x. So you want to end up putting f of x in parentheses. So I think for this one, just so we don't make the mistake later on, I'm going to start with the transformation rule. So it's g of x equals 5 times f of x. And then we're going to take f of x, which is cosine of 3x plus 1, and put it in here. But since there's multiple terms there, I'll have to put it in parentheses. So it'll be 5 times cosine, you can use brackets if you want, cosine of 3x plus 1. And then when you're distributing in the 5, I'm actually going to change these to brackets. When you're distributing in the 5, you'll multiply it by the front of the cosine, but you never multiply or distribute into the argument. So you would not multiply by the 3x. You would skip over the 3x because that's a part of the argument. We're not going to change that. Think of like these parentheses kind of like gel cells. Nothing is going in or coming out of it or simplifying into it. So we just need to multiply the 5 out in front, and then we just can't forget to multiply the 5 by the 1 as well. So it'd be g of x equals 5 and then cosine of 3x, that's not going to change, and then 5 times 1 at the end, so plus 5. So I'll say like this gets forgotten a lot, like remembering to multiply that 1 as well, so just be really careful about that. So it'd be g of x equals 5 cosine of 3x plus 5.